Hello everybody, I'm Michael Ralph, and today we're going to talk about using simulated trials to estimate confidence intervals. So let's get started. Let's start by taking a look at a system that is measuring time for a reaction to progress. This would be something that I'd use in a biochemistry unit. It could be a catalase floating disk lab or anything else where you can measure a time to benchmark in some reaction's progress. Now I've got 10 trials here from this reaction. And so now I want to analyze, or I want to establish, where would my confidence intervals be if this were to be my existing system that I wanted to then test a null hypothesis for some experimental condition. So I'm going to start by calculating the mean of my data set. And you're also going to want the standard deviation of that data set. Okay, and from here, we can go ahead and, knowing these two numbers, we can simulate having run this experiment many more times. The important thing here is that you must run enough trials to be confident that your measured mean and your measured standard deviation are very close to the true mean and true standard deviation of the phenomena. I've run 10 trials here. That's probably not going to be enough. You will probably want to compile a class data set because you need many numbers to be confident that this mean and this standard deviation is close to the true mean and true standard deviation. We want those to be as close as possible because we're going to assume that they are, and we're going to simulate many more trials of a system that does match that description. So I'm going to simulate some trials, and if we're simulating, we can take advantage of the computer's speed to simulate not 3, not 30, let's do a great many trials. Let's do 600, why not? And for each of those, I'm going to use the function that is norm, the normal distribution, and I want to use the inverse form of that function. And the probability, this we want to be random. The mean, we will just direct it to our measured mean. Don't forget to lock it because we will be copying and pasting. And the standard deviation, do the same thing. And then close. And it'll give us a randomly generated trial within a system that matches those measurements. And then we'll copy and paste it over. And then we're going to copy and paste it down. We're going to do many trials. Simulate doing this 600 times and 10 trials in each one of those simulated experiments. And then for each of these, we want to calculate the average. And we're going to calculate just the average of each one of those independent replicates. And copy and paste that all the way down. And then when I actually rerun this, you'll see that because I've included randomness in the probability, I have lots and lots of new trials generating new numbers to simulate this system, having done lots and lots of trials. So from here, we're going to start to describe that data set because what we really want to know is what's the likelihood of various events happening. So the min and max will be useful. So there are functions for min and max of our means. So let's get descriptions of that, and it's going to be helpful in the next step is why we want to do this. So I see how high and how low this goes, and so now we're going to go back to our bin methodology to see how frequently various means occur in this simulated data collection step. So our bins, we're going to start at, we see that it never goes below 8.5, so let's start at 8.5. And between 8.5 and 14-ish, I'm going to say probably half second is a good bin size. And I want to make sure I cover all of my data so it never goes above 14.5, so we'll stop there. And then for our count, remember we're going to use our frequency tool that we have done in a past video. Frequency in our data array is this set of means. And our bin array is this set of bins. Close the parenthesis, and remember for this one we need to hold Control and Shift and then hit Enter, and it'll fill in all of our numbers. Let's do a spot check and make sure all of our trials have showed up in our array. This independent check is always a really good idea. And then we'll calculate some frequencies, which is just number of events that we like divided by total number of events. Don't forget to lock that in number, and then copy and paste it down. And then remember, I like to make it nice and pretty by converting it to percentages And now we get a nice description here. And then our last step is to visualize the distribution of those events and help Excel label it properly. And there we go. And so now, as I run lots and lots of simulated trials, you'll see how likely various means are to occur in that system. And so from here, we can estimate our confidence intervals. And looking at this distribution, it looks like we're going to cross somewhere about there for over the mean and somewhere about here under the mean. Somewhere about there. So we've got our upper and lower confidence interval levels. There's another way to do this estimate given this type of measurement. We can use standard error. So standard error is take our standard deviation and we're going to divide it by the number of the square root of the number of samples. So I've taken 10 samples here, so Excel can do square root, and there are 10 trials in this data set. And then our confidence intervals are 2 standard errors away from the measured mean, both above and below in this situation. So we're going to do our mean, and I'm going to lock it. And lower will be subtraction, minus 2 times our standard error. Lock that as well. And then I'm going to paste that down and just change it from a minus to a plus. And I've got upper and lower confidence intervals. So 9.85 we can see is a little bit off for our lower, and our upper 13 and change is actually very, very close. So they're just another tool in your toolbox. It's a lot faster to do than doing a simulated trial, so it's another way to just estimate where those confidence intervals probably lie. So we can either do standard error or we can do our simulated trials.